Okay, let's take a look at stoichiometry in the real world. Access, limiting amounts, percent yield, and impurities. In the warm-up it says, suppose you're working in an ice cream shop and a group of customers come in and they want to order ice cream sundaes. The shop's computer page reads as follows. For scoops of vanilla ice cream, there are 6 scoops. For chocolate syrup, there's 200 mils. For super sweet red cherries, there's 475. And for the sundae recipe, we have a scoop of vanilla ice cream, 50 mils of chocolate syrup. This should be a capital L here. 1 cherry on top. And we're going to come down here to these questions. It says, what is the maximum number of sundaes that you could make for customers? So based upon the number of items that we have available, I would say we could make 4. What item limits the number of sundaes that you can make? Well, the chocolate syrup, I think, is going to limit how many we can make. Number 3, how much of each of the excess items will still be left as sundae stock? Well, you're going to have 2 scoops of ice cream left, and you're going to have 471 cherries. Okay? So we're assuming during a chemical reaction that the reactant provided is totally pure and that it is completely consumed. And that there aren't any side reactions that may happen, and that all of the reactants are consumed completely in stoichiometric quantities. That means based upon the mole ratio that's provided, it should be identical to that that you're given. Now, 1 or more of the reactants is likely to be in excess. That means that you'll have more than enough of it to completely react with another, so you won't run out of it. And if we go to the next page and we take a look at this quick check, you'll see that we have 2 carbon monoxide combining with oxygen to produce 2 carbon dioxide gas. And they want to know which of the reactants is in excess. So if I have 2 of these carbon monoxides reacting with 1 O2, and these 2 carbon monoxides react with another O2, I'm going to be left with an O2 in excess. Sketch any remaining reactants and products to show what will be present once the reaction is complete. So I'm going to end up with 1 O2. And number 3, how many carbon dioxide particles are formed? Well, I formed 2 carbon dioxide particles for each 2 COs that combine with an O2. So that means that I'm going to end up making 2 COs plus 1 O2 gives me 2 CO2, and then 2 COs plus 1 O2 will give me another CO2. So I'm going to end up forming 4. How many excess reactant particles remain? There is 1. So the reactant that is totally consumed, which in this case would be the carbon monoxide, that is called the limiting reactant or reagent because it limits how much product can be formed. And the reactant that remains is known as the excess reactant. It is not completely consumed. Now, if we take a look at this, let me erase this really quickly. What we're going to do is we're going to move over to the practice problems here. Because you have essentially learned almost all of the math pertaining to this section. It's just terminology that we need to explain. So let's take a look at practice problem number 1. It says we have 25 grams of zinc metal and it's reacting with hydrochloric acid. You're going to produce hydrogen gas and zinc chloride. This is your balanced chemical reaction. If I have 25 grams of zinc and I have 25 grams of hydrochloric acid, what volume of hydrogen gas at STP is formed and what mass of excess reactant is left over? Okay, so when you have the quantity of two reactants, it's automatically a limiting reactant problem. They may not tell you that. Okay, they want you to realize that when you're given the quantities of two reactants, you have to calculate how much each reactant will produce of that product, and then you have to determine from there whatever they're asking. So what we're going to do is we're going to take our 25 grams of zinc, we're going to convert that to moles by dividing by its molar mass. The coefficient in front of zinc is a 1. The coefficient in front of H2 is a 1. And then I'm going to liters, and I'm at STP, so I can use 22.4 liters per mole. That's going to give me 8.57 liters of H2 produced by zinc. I have to do all of that work with and I'm going to do it down here, with the HCl as well. So I have my 25 grams of HCl. The molar mass of HCl is 36.46. I'm going to do a mole ratio, 2 moles of HCl for 1 mole of H2. And then convert to liters of H2. And I'm going to produce 7.68 liters of H2 from my HCl. Now I'm going to point a couple of things out to you. This was with zinc as my reactant. This was with HCl as my reactant. You want to look and see which reactant produced the least amount of product. 7.68 is less than 8.57. We would call this the theoretical yield. Okay, so whatever reactant produced the least amount of product, that reactant is my limiting reactant. That means I will run out of that reactant before I can make any more product. And this is how much hydrogen I should produce if I were to do this in the lab myself. Now, the zinc reactant is in excess. Okay, that means I'm going to have a little bit of it left over. Now, what I need to do is figure out the mass of excess reactant left. So this 7.68 liters is the volume of gas that I should make in the lab. That's the maximum amount I will make. To figure out the excess reactant that's left over, what you have to do is you need to take the limiting reactant and you need to convert it to the excess reactant to figure out how much of it you will use. So we're going to convert this over grams to grams, grams of HCl to grams of ZN. Okay, so the 25 grams of HCl that you're given, that limiting reactant, will use 22.4 grams of zinc. Okay? Now, how do I figure out how much is left? You want to take the amount of zinc that you're given, which is 25 grams, so the 25 grams of zinc that was given, and you want to subtract the 22.4 grams of zinc that was used. And that will give you 2.6 grams of zinc left. Scan the QR code for number 2 with your phone and write the work down. We're going to go to practice problem number 3. For number 3, it says when ammonia is passed over hot calcium, calcium hydride and nitrogen gas are formed. So the balanced equation here is 2 NH3 plus 3Ca forms 3CaH2 and N2. What mass of calcium hydride results when 20 liters of ammonia is measured at STP and 150 grams of calcium react? What quantity of excess reactant remains? Okay, so there's a lot going on here. This is a limiting reactant problem because you're given the quantity of 2 reactants. That means you have to convert each reactant over to the product to see which produces the least amount of product. So we're going to start out with our 20 liters of NH3. We're at STP, so we can convert that to moles using 22.4 liters. The molar mass of CaH2 is 42.1. You're going to get 56 grams of CaH2 there. Now what we're going to do is we're going to take our 150 grams of calcium and we're going to convert that to moles. And then over to grams, and you're going to get 158 grams if you use that as your reactant. So what does this mean? Remember, we're looking for the least amount of product produced, which in this case is 56 grams. So this is called the theoretical yield. This is how much you should make. It's the maximum amount of product that you could make because you're going to end up running out of NH3, which means NH3 is my limiting reactant, and that tells us that my calcium is my excess reactant. Okay, so I'll have some calcium left over. So the mass of calcium hydride that we make is 56 grams, and we want to know what quantity of excess reactant remains. So what we're going to do is we have to convert the limiting reactant to the excess reactant to see how much of that we will use. So I'm going to put the excess calculation down here. So we're going to start with our limiting reactant, NH3 being converted to moles. And that is 2 moles of NH3 for every 3 moles of Ca. And that will give you 53.7 grams of Ca. This is how much will be used by the NH3. So how much remains? Well, we were given 150 grams of Ca. So take your 150 grams of Ca that was given to start the problem, subtract 53.7 grams of Ca that was used, and that's going to give you 96 grams of Ca remains. Okay? Okay, we are going to go on to the next section here. Let's talk about percent purity. So for percent purity, it's really impossible to obtain a chemical that's in pure form. And you're commonly going to have the percent purity indicated. And percent purity by mass is the mass of the pure chemical divided by the mass of the impure sample times 100. And there are several types of calculations involving impurities, and the most common are with an impure reactant. It's a more difficult type that gives a quantity of product and requires the use of this value to determine the percent purity of a reactant. We are actually not going to use this concept here, so we're going to go ahead and move over to percent yield here. Okay, so percent yield is, well, it's considering another one of the assumptions we made at the beginning. Reactions don't always go entirely to completion. What that means is all of the limiting reactant doesn't necessarily always get converted into the product. And sometimes we might be left with a little bit of limiting reactant remaining. So in real life, this is sort of the case. And some reactions will complete themselves partially. So the percent yield is the amount of product that you obtained divided by the amount of product expected times 100. And the amount of product expected, this right here on the bottom would be your theoretical yield. This would be what you calculated, what you expected to make, okay? And let's turn to the next page and take a look at some practice problems here. We have zinc metal reacting with an excess of hydrochloric acid solution. So this is going to be Zn plus 2HCl to produce H2 plus ZnCl2. We've got a 7.23 gram piece of zinc producing 2.16 liters of hydrogen. So this is your actual yield that they told you in the problem. And they told us that we are at STP. Okay, and that hydrochloric acid is in excess. So this is not a limiting reactant problem, but if they want us to figure out the percent yield, we need to figure out the theoretical yield because that's part of its equation. So I'm going to take the 7.23 grams of zinc, and I'm going to convert that to moles. And then I'm going to do a mole ratio from zinc over to hydrogen gas. And then since I'm at STP, I can use 22.4 liters. And that's going to give me 2.48 liters of hydrogen gas. So this right here is my theoretical yield. That's how much I should make if I were to do this myself. What's the percent yield? Well, my percent yield is the actual, which is 2.16, over the theoretical, which is 2.48 times 100. Liters will cancel. I will get 87.1%. And I want you to scan Number 2, scan the QR code, watch the video, and write the work down for number 2. And we're going to go on to number 3. We have copper 2 oxide. I'm going to write this work up here. Copper 2 oxide is reacting with hydrogen gas. And this is going to form water and copper metal. There's your balanced equation. We've got 3.6 grams of copper metal obtained. This is your actual yield. And we've got a percent yield of 32.5%. What mass of copper 2 oxide was reacted with the excess hydrogen gas? Begin with a balanced equation. Okay, so what we should do here is we should take a look at, percent yield is the actual yield divided by theoretical times 100. So if I was told that my percent yield is 32.5%, 32.5% is equal to 3.6 grams over X, which is what I need to solve for, times 100. I can get rid of this 100 if I move the decimal 2 places over to the left. So this is going to give me 0.325 equals 3.6 over X. Now if you want to put the 0.325 over 1 and you cross multiply, then what we can do is solve for X. And you're going to end up with 11 grams of Cu for your theoretical yield. Okay, now what are we going to do with that? Well, we can use the theoretical yield to go back and figure out what the amount of our copper 2 oxide was. So if you take 11 grams of copper, whose molar mass is 63.55, and we do a mole ratio of 1 mole of copper to 1 mole of copper 2 oxide, and then we multiply by the molar mass, which is 79.55. That will give us 14 grams of copper 2 oxide. And that is the mass that we began with. That's how much that reacted.